Let's imagine that we've got some object with a volume that's got three dimensions, L1, L2, L3. And this is the initial size of the material. We then increase the temperature, so we let the temperature increase by, say, let's say some amount delta T. So what happens? Well, this side will increase by some length delta L1. This side will increase by some amount delta L2. And this side will increase by some amount delta L3. So our new volume, the initial volume L0, is just L1 times L2 times L3. But the new volume is now the new length here, which is L1 plus delta L1, times the new length here, which is L2 plus delta L2, times the new length here, which is L3 times delta L3. And that's going to be our new volume. Now the new volume is just the old volume plus an increase in volume, so we'll say that this is V0 plus delta V. Now what is this? Well, let's multiply all the first terms, L1 times L2 times L3, so we got L1, L2, L3. Now let's do all the terms that have one delta value in them. So we'll take L1 times L2 times delta L3, L1, L2, delta L3. Then we'll take L1 delta L2, L3, L1, delta L2, L3. And then we'll take delta L1 times L2 times L3. And then we have all the terms with two delta terms. And then finally the last term with all three delta terms. Now, let's just think about this for a second. What we expect is that the delta L is small compared to the initial length. We found that for 1 kilometer, for a very big temperature change from a cold day to a hot day, cold day in winter to a hot day in summer, the change in the length of that was about half a meter compared to 1,000 meters to start with. So the delta L is small compared to the initial length. And in general, that's going to be true, again, as long as the temperature changes are not too large. So we expect the deltas to be much smaller than the initial length. But let's think about this just for a second. What is V0? V0 was L1, L2, L3. So let's remove the V0. That's this part, L1, L2, L3. So we have that delta V is these terms, okay, with the single delta term. And these are all going to be small terms, the delta L's. If we included the terms with two delta L's, that would be the product of two small numbers, which are going to be much smaller than these terms. And the term with three delta L's will be even smaller than those. So, to a very, very good approximation, if we just keep the terms with one value of delta, it's going to give us a pretty good estimation of what the change in the volume is. So we'll just take the single terms, the terms with a single value of delta. So what's delta 3, delta L3? That's going to be alpha L3 delta T. So we've got L1, L2 times alpha L3 delta T. And what's delta 2? That's going to be alpha L2 delta T. So alpha L1, L3 times L2 times delta T. And what's delta L1? That's going to be alpha L1 delta T, and then times L2, L3. Well, we notice these are all exactly the same, these terms here. So it basically gives us 3 alpha times L1, L2, L3, which is our initial velocity, initial volume, V0, times delta T. Well, if we were to write this in a form similar to what we had before for the linear expansion, we have that delta V equals some quantity, we'll call this beta, times the initial volume times delta T, where beta is what we call the coefficient of volume expansion. And what do we notice? We notice that beta is equal to 3 times alpha. So the coefficient of volume expansion is just 3 times the coefficient of linear expansion. It's a very, very simple relationship. Remember, it's an approximation because we are assuming that all of these changes in the volume for two values of the delta terms are much, much smaller than these. So this is a good approximation for the volume expansion. I would like to stick some numbers in here, but I'm going to leave that for the homework because I really want to move on. There is so much I want us to do. So let's take a look at something else. So let's imagine we've got some sample of a material, and we've been talking about the temperature of this depends on how much energy, internal kinetic energy it has. So if we wanted to heat this thing up, if we wanted to raise the temperature, what would we have to do? We would have to add some energy to it. And not just any kind of energy, not like throwing it for kinetic energy. We want to talk about heating it up, so the energy that we want to add is some amount of heat. We add heat to the object. The amount of heat that we refer to, we typically use the letter capital Q to represent an amount of heat. So we add an amount of heat, Q, and the temperature increases by some amount, delta T. My question now is, how are these related? How is the amount of heat related to the temperature increase? Well, let's think about that. What sorts of things will affect the temperature change? Well, we expect the temperature change to be related to the amount of heat we add. The more heat, the more temperature increase we get. So we expect delta T to be related to Q. And as long as, again, we don't put too much in, we expect it to be linearly related. Double the amount of heat, double the temperature change. What else? Well, what about the amount of material? We expect maybe a larger material to have a smaller increase if we put some amount of heat into it. If we have a smaller material and we put the same amount of heat, we would expect a bigger increase. So we expect the temperature change to be dependent on the mass, perhaps. There are different ways that we could describe this. We could talk about the mass of the material, the number of moles of the material, the number of particles the material has, or the volume of the material. There are different ways of doing that. We are going to look at the mass. We're going to use the mass as our measure of the amount of material. So the larger the mass, the smaller the delta T for a given amount of heat. So delta T we expect to be related to 1 over the mass. And then again, we expect it to be dependent on the material. Some materials will have a smaller increase in temperature for the same Q. Other materials will have a larger delta T for the same Q. So somehow this is going to be dependent on the material. Well, we'll write this as an equality, but rather than delta T equals something, we'll write it as Q equals something. So bringing the M over here, the dependence on the material over here, we're going to write this as Q equals M delta T times the material dependence we're going to write as a letter C, where C is called the specific heat capacity. And that is going to depend on the material. So different materials will have different heat capacities. Okay? So let's stick some numbers in here and see what we get. Let's imagine that we start with 250 grams of liquid water at 20.00 degrees centigrade. And now let's imagine we add some heat to it. So I'm going to add an amount of heat that's equal to 1.00 times 10 to the 4th joules. And let's see if we can figure out what's the final temperature of the water. Well, what do we know? We know that Q equals mc delta T. Delta T is then Q over mc, which is, okay, Q, we've got 1.00 times 10 to the 4th joules over the mass. We'll put this right into SI units. 0.250 kilograms times C, the specific heat of water. For this particular problem, we need to know what that is, or we wouldn't be able to calculate delta T. So I'll give you the specific heat of water. It's kind of strange. Different textbooks that I have looked at have slightly different values, but the value that I will use in all of our calculations is 4,100, make sure I give you the right number, 4,186. And the units are joules per kilogram degree Celsius. Joules per kilogram degree Celsius. We'll see how those work out. Okay, so let's notice. We've got joules, canceling joules. We've got kilograms, canceling kilograms. And we end up with degrees Celsius, which is what we'd expect for a change in temperature. We multiply this out, and we find that delta T is equal to 9.56 degrees Celsius. Now, what is this? This is the temperature change. This is the amount that the temperature has increased because we've added heat. So the temperature increases by 9.56. Starting at 20.00, we then have our final temperature will be 29.56 degrees centigrade. So there we go. So we can use this Q equals mc delta T. We could use this to find the change in temperature. If we knew the specific heat of the material, we could use it to find Q, or we could use it to find M, or if we didn't know C, if we knew the others, we could use it to find the specific heat of the material. I'd like to do another example where we actually do that. See if we can figure out what is the, We're going to assume another value, and we're going to try and find the final temperature when we mix two things together. Let's see if we can do that.